This is 2010 FRQ number 2 in the calculator section. A zoo sponsors a one-day contest to name a new baby elephant. Zoo visitors deposit entries in a special box between noon, t equals 0, so this is noon, and 8 p.m., 8 p.m., all right? Number of entries in the box after noon is modeled by a differential function e for t between 0 and 8. Values of e of t and hundreds of entries at various times are shown in the table above. So at noon, this is how many entries. At 2 p.m. we have 400 entries. At 5 p.m. we have 1,300 entries, and so on and so forth. Okay, so use the data to approximate the rate in hundreds of entries per hour at which entries were being deposited t equals 6. So right here, show the computation that leads to your answer. So we're looking for the rate. This is how much is already in there. So you're looking for the rate of it. You will use slope. Very simple. You take y2 minus y1 over x2 minus x1. So in part A, you want the rate at t equals 6. So that equals e of 7 minus e of 5, 7 minus 5. That's my y2 minus y1 over x2 minus x1, 21 minus 13 over 7 minus 5, 8 over 2, 4. It's not 4 entries, it's 400. So 400 entries per hour. This is the rate at which this is happening. Okay? Part B. Use a trapezoidal sum with 4 subintervals given by the table to approximate value of 1 over 8 integral of e to t dt. Using correct units, explain the meaning of this integral in terms of the number of entries. This is the average number of entries between 12 to 8 p.m., right? So we're going to use our trapezoidal sum to do this. So the problem is, again, you cannot use your formula because the difference between these two are not the same consistently. This is our height, these are our bases, all right? So let's do our integral first. So the integral between 0 to 8 e t using trapezoid is going to be, here's the first trapezoid, 1/2 times the height of 2, and then base 1 plus base 2, 4 plus 0, all right? Next, plus 1/2, the height between these two is 3, and then base 1 plus base 2, so 13 plus 4. 1/2, difference between these two, the height of 2, times base 1 plus base 2, 21 plus 13. Last one, 1/2, the height between these two is 1, times base 1 plus base 2, 23 plus 21. Okay, so the total here would give us, if you plug everything in the calculator, it would give us 85.5. Now the average of that is over 8 hours here. That's why it's 1 over 8. So 1 over 8 times 85.5, that would give us 10.6875. And that is the average number of entries between noon and 8 p.m., right? That's an average because you're taking the integral over the 1 over b minus a, okay? All right, at 8 p.m., volunteers began to process the entries. They process entries at a rate modeled by the function p of t, so this is the rate at which they're processing it. Hundreds of entries per hour between 8 to 12 p.m. According to the model, how many entries had not yet been processed by midnight? All right, so how much did they process, right? So how much did they process? So they processed integral of 8 to 12 of t cubed minus 30t squared plus 298t minus 976. So an integral of this p of t, right? Put it in that calculator, dt, of course. You really don't need a calculator to do this, but it is possibly a little bit faster. So math 9, my function of t cubed minus 30t squared plus 298t minus 976, comma, x, comma, 8, comma, 12. Close my parentheses. And you get 16. Very nice. 16. Not 16 entries, 1,600 entries, right? So we have already taken 1600. This is what is processed. So by midnight, they processed 1600 entries. However, at the end of the competition, you had 2300 entries. So 23 minus 16 equals 7. So 700 entries yet to process. Right? You're only able to process 1600. You still have the 23 total that you had at the end of the day. Okay, last one. According to the model from part C, so according to this model, at what time were the entries being processed most quickly? All right, so most quickly means fastest. Fastest means the most of something, right? So we're looking for the maximum of something, which means we're looking for P prime of T. All right, so P prime of T, when we're looking for the maximum of something, we set P prime of T equals 0. So let's take the derivative of that. You get 3t squared minus 60t plus 298 equals 0. All right, now this is not factorable. Don't waste time factoring it. So the quickest way of doing this, well, one of the quicker ways. So 3t squared minus 60t plus 298 is to graph this out. So I'm gonna go zoom 6 real quick. And, oh, I can see it's a little bit over on that side, and we don't care about the negative, so change my window. -2, put 20 on here, put a scale of 2, same thing, -2, 20 here, 2, graph. All right, so I can see I have 2 zeros there, so I go second calc, 0. Don't forget left bound is, for left bound of this point is above, and then right bound of that is under. And my first point is, when is t equals 0? T equals 0 at 9.184. And if you repeat the process again, you'll get t equals 10.817. All right, so now you don't know whether which one of these is the best, the quickest or the most, right? Because you have endpoints. So what you need to do now is compare the endpoint. P is only going from 8 to 12. So those are your endpoints. So your time, you have 8 and 12. You have these 9.184 and 10.817. So you need to compare your values. You plug them into your function, P of T, right? So P of 8. So you plug it in. P of 8 actually gives you 0 very nicely. And if you plug in the 12, you get 8. And if you plug in these numbers, these are the approximations, you get 5.0886, 2.91134. Yeah, and you can see of all these, this is the highest. That means it's processing the quickest, right? Because it is the most. So then you are processing fastest at t equals 12. Okay.